Okay, in this part of the lecture, we're going to continue looking at how electrical circuits work, and we're going to talk about something called Ohm's law. Now, here's the basic idea. Let's again consider our basic circuit of a battery or a voltage source, a switch, and a resistor. Now, what's going to happen is that when I close the switch, the potential difference created by the battery is going to make an electric field, and that's going to push charges down the wire through the resistor. If the resistor is a light bulb, it might light up. If it's a hairdryer, it might heat up a filament to provide hot air, and it might power a motor to blow a fan. But whatever is causing the resistance, it's converting that electrical energy into something hopefully useful. And so the charges, as the current flows through the circuit, as they pass through the battery, we've talked about they gain energy, they go through the wires, and as they go through the resistor, they lose energy. Now, the current is usually represented by the letter I. I'm not sure why they use the letter I. It's just what they use. It's very common in physics and engineering for the letter I to represent a current. And there's a relationship between how much current you get depending on how big your battery is or how big your voltage difference is and how big your resistor is. And that relationship is known as Ohm's law. And what Ohm's law says is that the voltage is equal to the current times the resistance. V is equal to IR. Now, of course, I could do some algebra and rearrange this. If I solve for I could rewrite this equation. That would mean divide both sides by R to get rid of this R, and I would find a different relationship that I is equal to V over R. And again, I stands for current, V stands for voltage, the voltage of the battery in this case, and R stands for the resistance. And of course, if I wanted to solve for the R, I'd divide both sides by I to get R by itself, and I would find that R is equal to the voltage divided by the current. And so all of these are equivalent relationships. And rather than just trying to memorize all three, it's better to know the sort of the proper form, the one that's in blue here, and do a little bit of algebra if you need to solve for one of the others. But these relationships, of course, all the same relationship, they're known as Ohm's law. And by the way, the resistor value, we know that the units of voltage are volts. The units of current are called amperes, or simply amps. Named after a Frenchman named Ampere who studied electricity. That's the name for the unit of current. V, of course, is in volts. And resistance is in what are called ohms. And so usually you see it represented by the word ohms. Sometimes it's represented by a symbol. And the symbol for ohms is the capital Greek letter omega, which looks kind of like that. That's an omega. And so if you see that symbol, usually that's referring to ohms. Amperes. Now, just a reminder, when we're talking about electrical resistance, we've talked about how conductors have a low resistance and insulators have a high resistance. And so that is the value in the number of ohms for a particular material is going to be either low or high, and that's what you plug into that equation as the resistance, or the letter R. And so, again, we have Ohm's law, and I've written it out in words this time instead of the math symbols. The voltage is equal to the current times the resistance. That's Ohm's law. All right, let's look at a quick example. This is sample problem 1, and this is actually straight out of your textbook. It says, how much current flows through a lamp with a resistance of 60 ohms when it's connected to a voltage difference of 12 volts? So we have the relationship for Ohm's law here. Which one of these three are we looking for? Are we looking for the voltage, the current, or the resistance? Obviously, we're looking for the current. It's asking how much current is flowing. And so we need to get I by itself. if we divide both sides of the equation by r, we get v over r equals to I times r all over r, and then the r's will cancel, and I'm end up with what I want. The current is v over r. And so that's what I can see here. The current is the voltage divided by the resistance. And so if I plug in 12 volts here and 60 ohms there, I get a current of 0.2 amperes or 0.2 amps. And that's the answer to the question. That tells you how much current will flow through that circuit. Let's look at sample problem number 2 now. It says a toaster oven draws a current of 12 amps. So we're not looking for the number of amps, we're given it. So we're not going to be looking for current. And it says when connected to a voltage source of 120 volts, what is the resistance of the toaster oven? So we're looking for R. So again, we want to get R by itself. And so in order to do that, we can divide both sides of the equation by I. And when we do that, over here, the I's will cancel and we'll have R by itself. And we get the resistance is the voltage divided by the current. R is V divided by I. And so I can see I've written that out in words here, and I just plug in the numbers. 120 volts divided by 12 amps of current. That gives me 10 ohms of resistance. And remember that funky omega, that's just a symbol that means ohms, the unit for resistance. Let's look at another example. The resistance of the human body is typically around 100,000 ohms. If they touch the opposite ends of a 12-volt battery, how much current should flow through that person's body? So if you touch the positive and negative terminals of a car battery, are you going to be electrocuted? Probably not, but let's look and see. So we've already seen that if you want to solve for the current, you get voltage divided by resistance. And so here I'm going to divide 12 volts, which is a small number, by 100,000 ohms, which is a big number. And I find that the current is very, very tiny. It's not even 1,000th of an amp. It's like a 10,000th of an amp. It's very, very tiny amount of current. You wouldn't even feel that much current. Now here we can look at that same situation, a person touching the opposite ends of a car battery, but what if their skin is moist when they do it? If your skin is wet, that actually lowers the resistance of your body, and it can be reduced to as much as 1,000 ohms. So why would you be wet? Maybe it's raining, maybe it's really hot out and you're sweaty, maybe you've gone for a swim. It doesn't really matter, but if your skin is wet, the resistance of your skin can be greatly reduced. And how much current would flow then? Well, it's the same formula, voltage divided by resistance, but here we're dividing by 1,000 ohms instead of 100,000 ohms, and the answer is quite a lot bigger. And this is actually enough to shock you. It would not be a pleasant experience to touch the opposite ends of a car battery when you're wet. And so let me just state for the record, I am not suggesting that you go out and touch the opposite ends of a car battery, because if the conditions are bad, you could actually get shocked by it. But, it's going to depend on what your resistance is as to how much current flows through you. And that's what actually shocks you. It's not the voltage, it's the current. Current is what can harm you. Voltage can't harm you, except in so much that a voltage difference can push a current. And so if the current being pushed through you is really big, then you're going to be hurt by the electricity. But if the current is very tiny, you won't even feel it. Here we see a nice chart, which I took from your textbook, and it's kind of showing the effect of different amounts of electric current in the body. So 0.001, that's bigger than touching the car battery when you're dry. That's actually where it's getting big enough to be felt. At about 5 times that much, it starts to be painful. 0.01 amps, that's when you start getting involuntary muscle contractions. Involuntary muscle contractions, what's that about? Well, you probably know that your muscles are powered by electricity. That is, there are electrical signals that go from your brain to your muscles that signal them to contract. And so if you have other current going through your body, the muscles will contract in the same way as if the electrical signals were coming from your brain. And so sometimes you see in movies someone touches a wire and they get electrocuted and they can't let go of the wire. That's because as they've grabbed a hold of the wire, as the electricity is flowing through their arm, the muscles in their hand and their arm are clamping down. They can't let go and they get electrocuted by it. As it gets higher, you get complete loss of muscle control. And if the current gets high enough and if it goes through your heart, it can actually disrupt the rhythm of your heart and cause a heart attack. So electrical safety is a very, very important thing to consider if you're dealing with electrical systems, because if the current going through you gets high enough, it can injure you, it could literally kill you. And so if you're ever in a situation dealing with electricity, please leave it to an expert. And there are a couple of other figures here that I lifted from your textbook. I want to go over what they're talking about because they're kind of odds and ends things, but they're important to understand. And so in the picture on the left, you can see there's a bird hanging on a high voltage electrical wire. And you've probably seen this all the time. You've seen the high voltage wires carrying electricity from the power plant to your house or your school or wherever. And sometimes you see birds landing on them. I'll tell you, sometimes those wires, they can get up to 20, 30,000 volts potential. The voltage of them is many thousands of volts. And yet those birds don't get shocked at all because it's not voltage that makes current. Do you remember what it is that makes current? It's not voltage, it's differences in voltage. And so if this wire is 10,000 volts here and 10,000 volts there, then there's no difference, and so there'll be no current going through this bird. But if the bird takes his foot off of this wire and grabs a hold of the wire over there, if this guy's 10,000 and this guy's 5,000, there's suddenly a 5,000 volt potential difference from one end of the bird to the other, and you might end up with a barbecue bird if you do that. Or if the bird does that. Because again, it's not the voltage that drives the electricity, it's the voltage difference. The next thing that we can talk about here is a typical plug. Now, when you plug a plug in your house, some plugs just have two prongs, and usually when they just have two prongs, unless they're very, very old, one prong is fat and one prong is skinny, and that's so that you have to plug it into the wall a certain way. You can't turn it upside down. The reason for that is because if you have multiple things plugged in together, the voltages can stack and create big potential differences that could potentially shock you. But if you have them all plugged in the same way, it prevents that from happening. But a lot of plugs have a third prong, and that's the grounding plug. And literally in your house, somewhere there's a pipe with a wire that's hooked up to your electrical system that's buried in the ground. That's why they call it a ground wire. And what happens, if there's an excess of electrical charge built up, this third prong takes it to the ground. And so that is why you can have a ground wire. It also acts to prevent that accidental stacking of potential differences, which could be dangerous. But if you've ever been curious about that third prong, it's a safety feature, basically. It makes it harder for people to do dumb things with electricity that can get them hurt.